So Enrico is a PhD student with co-supervision from La Sapienza and École Normale Supérieure in Paris, I think, with the supervision from Giancarlo Ruocco and Francesco Zamponi. He's specialized in statistical mechanics and disordered system, and his research is focused on the relation between training algorithm, unsupervised training algorithm, and models of perception in neural network. And he will speak about training neural networks with structured noise that improves classification and generalization. So please, the floor is yours, Enrico.
Hi, thanks. Can you hear me, first of all? Because I never spoke. Okay.
Yes. I can hear you. I can see your presentation.
Perfect. That's grand. Thank you. So thanks for the invitation, first of all. Thanks for the introduction also. So this work has been conducted in collaboration with several people, which are indicated here. But I will specifically mention Marco Benedetti, who's a PhD fellow, who's moving to Bocconi very soon. And so the outline of the talk will follow the structure of the paper that I've been recently writing with Marco, which is currently under review. And so I will briefly introduce yourself to the world of attractor neural networks, which are models devoted to describing and explaining a bit associative memory, which is the property of some physical systems to retrieve previously stored information when an input is presented. Then we'll pass through some learning algorithms, so those processes of synaptic updating, which are responsible for the storage of the information in such networks. And that will go directly to the gist of the research, so the designing and the sampling of the best noise to inject in a learning process in order to enhance the associative memory performance of the network. Then we'll study a particular kind of noise, namely embodied in stable fixed points of the dynamics. And to conclude, I will conjecture a new learning palimpsest based on noise injection. So the type of networks that we're going to deal with are fully connected networks of neurons, where neurons are modeled by binary variable sigmas. As real neurons that can be silent or active, these variables can assume values -1 or +1, and such variables are connected with each other through some couplings, JJs, that we will consider to be symmetric for dynamical purposes. That would be rather clear in a minute, I guess. And these couplings really play the role of the synaptic efficacies, so the mutual signals that real neurons tend to exchange with each other. We avoid autopsies, so self-connections of a neuron with itself. And once you have these kind of networks, you want to see them evolve in time. So you want to see the configuration of the sigmas to evolve, because you assume that a memory retrieval process is a dynamical process. And so a kind of biologically plausible rule for the dynamics is the one indicated here, where the sigmas are updated depending on the sign of the total signal received by their neighbors. And this total signal is represented by this H variable, which in statistical physics is called local field of the neuron. Okay, so we assume the neurons to be updated one at a time. Okay, so asynchronously. Okay, in time, not all together at each time step. And we can start giving as an input to the dynamics configuration sigma. And we let it evolve, and after a certain number of steps, we'll see that it will stop, it will converge to a stable fixed point, to an attractor. And the existence of attractors is ensured actually by the symmetry of the couplings. Also, the symmetry implies that we have a Lyapunov function for the dynamics, of course, where local minima are, attractors are local minima of the same function, but this function coincides with the energy function that we can define for the system. So these attractors will have basins of attraction, so the collection of all the configurations that lead in the dynamics to the same attractor. And given this introduction for the physics, now we can define the rules of the game of the associative memory. So when we talk about associative memory, we want to define, we want to set a collection of special configurations, okay, that we call memories, which are these vectors, these binary vectors xi. And we generate at random p, a number of p memories, which is extensive in n and which is controlled by this load parameter alpha. And now we want two things. So the first thing is that these memories should be attractors. Okay, so we want to retrieve them perfectly by means of the dynamics. And the second thing is that we would like these attractors to, so these memories, sorry, to have finite basins of attraction. And we call this property, we call the first property classification and the second property generalization. So now we can benchmark the performance of the memory performance of the neural network depending on these two properties. And regarding classification, we can define the stability quantity delta I mu, and it's quite straightforward to recognize that classification is reached. So all memories are stable when all these stabilities are positive. Usually, these stabilities can be computed analytically for most of the neural networks models that are fully connected. But on the other hand, there's not an exact theory of the basins of attraction for fully connected networks. So in this case, we're forced to introduce a numerical observable, which is the retrieval map MF. So we consider an initial state of the dynamics, sigma 0, and then we compute the overlap M0 with one of the memories, okay? Then at that point, we run the dynamics until convergence, and we remeasure the overlap of the final state with the same memory, okay? So xi1. And in principle, we expect this function, mf of m0, when n, the size of the network is increasing, is becoming sharper and sharper, and it will become a step function signaling the typical radius of the basis of attraction to which the memories belong. So we fix the memories, and we require classification and generalization. And so to do so, what we can do is to optimize in a smart way the parameters of the network, so the couplings. And this is something that happens in nature as well with the plasticity processes that occur every time in our brain when we receive information. We want to maximize, our memory performance. So quite a old-fashioned, but yet still interesting, at least for the sake of physics, learning rule is the Hebbian learning rule. So according to this rule, a pair of neurons has a very strong interaction between themselves when the two neurons are all active or mainly active and inactive at the same time across a sequence of stimuli, so across the memories, okay? On the other hand, the interaction will be weaker if the two neurons are pretty uncorrelated across the memories, okay? And so by construction of this connectivity matrix, classification is never reached in the sense that memories are never fully stable according to the dynamics. But yes, for some values of alpha, which are smaller than a critical value, critical capacity 0.14, we have what we call memory retrieval in the sense that each memory has a non-vanishing overlap with the closest attractor. And this implies, of course, that we have a finite basins of attraction, and so we have a certain degree of generalization. So this Hebbian landscape at any alpha, it actually proliferates with attractors which are only weakly correlated with the memories, okay? And these attractors, which are so far from the memories, are called spurious states. And so one can imagine to start from the Hebbian landscape, out of the retrieval regime, so beyond the critical capacity, and then try to recover not only the memory retrieval, but also the classification property by removing the spurious states. So the intuition for the so-called unlearning algorithm is to remove some of these attractors to reinforce the memories, to make them stable. And actually, the intuition works in the sense that if you start from a random state, sigma 0, you run the dynamics, you reach a spurious state, and then you update the couplings according to this rule indicated here. After a few iterations of the algorithm, then you'll reach the scenario in which all the memories are stable. So you've reached classification. You can do it until a critical capacity, which is way higher than the Hebbian one. But still, the generalization properties for the network reached by this algorithm were not very clear so far. But I will give some insights in a few slides. Another approach to storage information is a supervised approach, and it's the one of the linear perceptions. And in this case, we have a set of constraints, so a set of requirements, okay? And we want to satisfy these requirements with a deterministic algorithm, okay? And the requirements in here, they want all the stabilities to be larger, not even than 0, but larger than a margin k, so a variable called margin, which is larger than 0. And so in this case, we initialize the system with any initial matrix, and then we update this. Then we perform this updating here, which is similar to a Hebbian update. But it has here a mask, which is symmetric. In this way, it symmetrized to have symmetric interactions, which assume a 0 value if there's nothing to do, okay? So if the stabilities are already larger than the margin k. It assumes a non-zero value. So in this case, the way I defined it assumes value 2. I missed a factor 1/2. So in this case, if the stabilities are smaller than k, you do something, okay, and you tend to align, okay, the patterns to the interactions. And after a few interactions, then you reach classification in the sense that all the constraints are satisfied, so the memories have become stable. And also, numerically talking, you can observe that the larger is the margin k, the larger the basins of attraction will be. So the generalization property will be. And so for each value of alpha, you can find a maximum value of k before losing the classification property. And we will call the linear perception with the maximal, so trained with the maximal margin, support vector machine, or SVM. Okay. So now we go closer to our goal. So I introduce a new algorithm. An algorithm that was invented by Elizabeth Gardner and collaborators as a kind of a version of a noisy perception. And the idea is that instead of you learn the memories not by teaching the network the memories themselves, but by teaching some blurry, some noisy versions of the memory. And the impressive thing is that, as we will be able to see, this algorithm includes within itself all the learning rules that we have seen before now. And so how does it work? So you can start from any matrix as well. And then at each step of the algorithm, you consider one memory, okay? So vector in the configuration space, one memory XIMU. Then you start sampling one noisy configuration, sigma mu. This noisy configuration is a random configuration that has a fixed overlap MT, which is a control parameter for the algorithm. So it's fixed. It has an overlap MT with the memory, okay? So the lower MT will be, the noisier sigma mu will be, because it will be very different from the memory. The higher MT will be, so the closer to 1 it will be, the less noisier this state will be, because it will be very similar to the memory, okay? So then you update the couplings in the following way, which really resemble the linear perception, the symmetric linear perception rule. But there's a difference, because in the perception, you want it to align the local field of the memory with the memory itself. In this algorithm, instead, what you do is that you want to align the local field of the noisy state with the memory, okay? And so as a consequence, you can imagine that we are creating a dynamic flux towards the memory. So we're making the gradients of the dynamics starting from sigma mu point towards the position of the memory in the energy landscape. Okay, and so Gardner thought that intuitively this would have enlarged the basis of attraction and would have set the memory at the very center of the basis of attraction. Okay, and this, in a way, this is what happens. But we computed the phase diagram of the resulting network, and we realized that things are a bit more complex. And so one can prove rigorously, given alpha, that when MT, so the training overlap, is 0+, so noise is maximal, then you recover a Hebbian network, okay, which has very poor memory performances. Then you can increase alpha and sorry, MT, and then you get into a phase which is really similar to the memory retrieval phase in a Hopfield model. So you don't have classification, but you can define some basins of attraction to which the memory belongs. And then eventually you reach another notable scenario, let's say, which is the one with MT equal to 1-, where also you can prove that the network converges to an SVM. So you have classification and maximal basins of attraction. So here comes our research question. In particular, we said, all right, let's use the training with noise algorithm. Okay, we don't change the algorithm itself, and let's fix the most extreme scenario that we can imagine. So the maximal noise, MT equal to 0+, the one that led to the Hebbian network with the standard, framework. But now we change perspective a little bit. We say, can we change the quality of noise, so the type of noise to learn, such that we can approach the performance of an SVM? So both classification and the maximal basins of attraction for a network, okay, which is kind of a low upper bound for associative memory models. And to do so, we rewrote in a suitable way the loss function of an SVM. I remind the audience the loss function is a function which is globally minimized by the training of the machine. Okay, so the goal is to minimize this function. And so, of course, we compute the gradient, the variation of the loss, according to the training with noise algorithm, okay, in the approximation of very small learning rate, lambda. And we realized that this gradient is a very easy expression. Let's say it's a sum of positive terms weighted by these omegas weights, okay, which are functions of both the training data that you're using at that time step and the stabilities that you reached at that time step also. And since you want this gradient to be strictly negative during learning because you want to minimize this function, we ended up with the optimal noise condition. Okay, so it's natural to see. I reminded you that these Gaussians here are very peaked around 0 because of this limit here. So the optimal noise condition says that the omega, so omega I nu, should be negative when whenever the relative stability delta nu is enclosed in a very narrow range centered in 0. Okay, and so this implies that the noise that we would like to use for training is no more IID. Okay, it's no more generated by a binomial process as it was in Gardner's case, but it's structured. So we need to have some internal dependencies in the entries of the noisy data points in order to ensure the minimization of the SVM loss. And so we asked ourselves, all right, but can I find this zoology, this kind of noisy data points in any landscape? Or there are some landscapes which are, more favorable than others. And so we probed different kinds of landscapes by means of a Monte Carlo at different temperatures. Okay, so we cut different altitudes of the landscape, and we saw whether the typical configurations were satisfying or not the optimal noise condition, let's say. And so we did it for the Hebbian landscape and for an SK model, so a complete random neural network where couplings are generated according to a Gaussian process. And so we plotted the average value of omega, okay, for delta equal to 0. Okay, we have a lot of data. We average the omega at relatively to the position here in this plot, delta equal to 0. Okay, and because that's the very important benchmark for the optimal noise condition. And so we realized that for the Hebbian landscape, this number here, this quantity is very negative for low temperature, and in particular it has an optimum which is not set at the stable fixed point, which is related to low altitudes, but still not fixed points in the landscape. On the other hand, the SK model doesn't work pretty well. It works better at high temperature. So when state become more random, which is pretty consistent with the fact that we were in this limit here, we recover the Hebbian network. And then the next step was to run another Monte Carlo procedure, but not to sample configurations on the energy landscape, but we wanted to sample the configurations that directly satisfied the optimal noise condition. Okay, so we started from in this circle here. We started in a Hebbian landscape, and we started the Monte Carlo on stable fixed points. Okay, and then in time we let the Monte Carlo sample the configurations that satisfy the optimal noise condition. And here on the left, here we plot the fraction of unstable directions, so the saddle index, so-called, of the sampled configurations as a function of the learning time. Here we perform the training with noise algorithm, and we see that most of the configurations that we sampled are not stable fixed points. They're not fully random states, but they are saddles, okay, low in the energy landscape, as we could imagine from the previous analysis. All right, so now instead we analyze an interesting case, which is the one where the noisy data are maximally noisy, but they are also fixed points. Okay, so we have MT equal to 0 plus always, and then we take noisy data to be fixed points. So in general, generally speaking, we can divide the update of the training with noise algorithm in two contributions. When MT equal to 0 plus, the first contribution is just noise, and it vanishes when the size of the network is large enough. The second contribution instead is what we call unlearning contribution, and it really coincides, with the unlearning rule when the data that we use are fixed points. Okay. And so the two algorithms in this scenario, converge with each other. They do the same job. And here on the right in this plot, we plot the minimum stability measured in the network at the given learning step. Okay, and we see that when lambda the learning rate decreases and the size of the network increases, the numerical measures are coincident. And here we also plotted the comparison between the obtained connectivity matrices, and we can say that they tend to the same object. Okay, so they do the very same thing. And this is consistent with some results that we had previously obtained from a numerical work from last year, where we compared an SVM with a network resulting from the learning algorithm. And we actually showed, consistently with our more recent analysis, that the retrieval map of an SVM is coincident with the one that can be measured through unlearning. And this result actually holds in thermodynamic limit, as we could see from some finite size scaling analysis. And here on the right, we show a projection of the path of the trajectory followed by the connectivity matrix, trained according to the two algorithms, so SVM in red and unlearning in blue. And you can really see that trajectories are very similar. They are, we measured that they end up in very close points in the space of trajectory. So the two algorithms are working at the same way. And there's another experiment that I've been performing, in this case with Rémi Monasson and Simona Cocco. So we apply the same concepts in a different kind of neural network, a continuous attractor neural network, which is a network which is usually employed to model spatial memory. So memory processes that are supposed to occur in the hippocampus. And these kind of networks are interesting because they can map positions in the Euclidean space in D dimensions to configurations in the neural space, so into points in the configuration space of the neural network. Okay, so this means that we can learn positions as memories according to our favorite learning rule, exactly like we did in normal attractor neural networks. But most importantly, we can map basis of attraction in the cognitive space to the Euclidean space. Okay, so we can see with our eyes the basis of attraction. And so we learned a grid of positions like indicated here with the Hebs rule. And you can see that basis of attraction, they're not centered. So each color is a different position. They're not centered on the position at all. They're very regular. They're even intermittent in space. Okay, but when we performed the unlearning and the SVM, of course, there was a completely different story. So we reached bases of attraction that were very well centered around the memorized position. And as we can see, the bases of attraction are maximal because they are well packed in space, and they even have their fractal dimension in the Euclidean space. As we can see, the results for unlearning are very similar to the SVM as our, optimal noise condition analysis would have suggested. And so I conclude with conjecturing a new learning paradigm which is entirely based on learning noise. Okay, and I start from some empirical observations. So first of all, the brain should be effective in both classifying objects, let's say, and in terms of generalization. And there are some regions of the brain which really seem to behave like perceptrons, even though the perception rule is not biological at all, because it's completely supervised. And I could mention works by Nadal and others regarding the Purkinje cell, etc. Then we know from other studies, mainly from neuroscience, that night sleep is important for memory formation and memory consolidation. So there are important processes, synaptic processes occurring in the brain at night. And also we should mention that noise injection is a super frequent technique in multi-layer neural networks, which are the ones used for deep learning. And there are data augmentation or dropout techniques which really help in avoiding overfitting and increasing generalization, even though there's not a very consolidated theory-based criterion under their use. And so I want to link a bit the points by introducing this new procedure. So imagine that all the learning is performed by training with noise. Okay, so the algorithm that we have been used, that was invented by Gardner. Then all the data are maximally noisy with respect to some memories that we will call archetypes, neurons. And then we can imagine that learning occurs in two phases. Okay, so the first phase is an online phase where we learn. So it occurs in the open air, and we learn external stimuli. Okay, so we can start our brain, let's say, from a tabula rasa, so zero couplings, and then we can imagine that we receive stimuli from the environment, and we ambitiously assume that the stimuli encode in themselves some symmetry, some concepts, some ideas, okay, that we call archetypes, which are pretty orthogonal with each other, but with respect to which the real data can be imagined as random maximally noisy data, okay, like the ones that Gardner used for the original algorithm. So as we know from theory, when we implement the training with noise algorithm, we end up with a Hebbian network which is out of the retrieval regime, so completely useless in terms of associative memory. But then we have an offline phase where we sample from the Hebbian landscape some structured maximally noisy data, using, for instance, some dynamical processes. And then we learn this noisy data with the same algorithm, with the training with noise algorithm. And we expect that in at night, for instance, if we want to be poetic in a way, our network will consolidate some basis of attraction around these hidden archetypes that we didn't know. We just knew they were there, but we didn't know them. And we can imagine that these archetypes are really the fundamental, important information that we should extrapolate from the environment. And with this, I want to conclude, and I'm ready to take questions if you have any. Thank you very much.
Thank you very much. Are there comments or questions? Can you say something more concerning the optimal features of the noise? When you said,
you're talking about the optimal noise condition here.
Yes, yes.
Yeah. So the physical interpretation of these omegas are a bit foggy, but still we can try to push an interpretation. I have a backup slide about this. So you can imagine the linear perception learning written like this. Okay, so you update the couplings of the network as plus a vector. So in this case, the couplings. So we are dealing with the rows of the connectivity matrix. Okay, so you can always imagine the training of a perception as a rotation of vectors. Okay, geometric rotations, and you are rotating the JI, so the rows of the connectivity matrix, to align them with the memories. Okay, in that case, you'll reach classification. And so to do so, you can imagine the update of the couplings as this rule here, where this eta vector is a new vector, which is basically a gauge transformation of the memory. So it's a eta I mu vector is xi I mu times the memory, the muth memory. Okay, so then you can let's consider stable the noise as stable fixed points, so we can approximate the training with noise algorithm with the unlearning algorithm. You can rewrite the unlearning algorithm exactly in the same way, but instead of using the memories, you use the spurious states. Okay, so you have this rule, okay, which is it shows you a rotation of the vectors in this gauge transformation of the configuration space. Okay, and then you realize that the scalar product between these two updates, this is minus omega I mu. Okay, so omega mu is an overlap between the updates in the couplings. And so since you want this scalar product to be positive, because you want the unlearning to act like a perception, okay, in particular way, like a maximally stable perception, you want this object to be positive. And as a consequence, you want this omega to be negative. Okay, this is something we already knew from our numerical work from last year, but a new information that was given by the new way we record the optimal noise condition is that we just need to satisfy this condition, okay, so omega to be negative, when the stability for a short number of stabilities, let's say, for when the stabilities are very close to be null. Okay, for the other values of I and mu, for the rest of the stabilities, you don't care. You could have any values of the omegas in principle.
Okay, thank you. Any other question? Comment? Seems that there are no other questions, so thank you very much.
Okay. Thanks to you.
And thank you for all of you that are still there. And this and the seminar. And I mean, this is the last seminar of this academic year, let's say. We will restart in September with other 2 seminars on the 14th of September. So have a good summer, all of you, and see you in September. Bye-bye. Thank you.
Thank you, Rosario. Bye to everybody. Grazie Enrico, grazie Rosario.
Thanks, yeah.
Bye.
Ciao.
Bye.
Ciao Rosario, grazie.
Grazie a voi, ciao, grazie Riccardo.